All right, welcome to the Neuralink product demo. I'm really excited to show you what we've got. I think it's going to blow your mind. So the primary purpose of this demo is actually recruiting. So I'm going to emphasize this at the beginning and then again at the end. We're not trying to raise money or do anything else. The main purpose of this is to convince great people to come work at Neuralink and help us bring the product to fruition, make it affordable and reliable, and such that anyone who wants one can have one. And so I want to emphasize the purpose of Neuralink. Like, what's our goal? Our goal is to solve important spine and brain problems with a seamlessly implanted device. So you want to have a device that you can basically put in your head and feel and look totally normal, but it solves some important problem in your brain or spine. And the reality is that almost everyone over time will develop brain and spine problems. These range from minor to very severe, but if you live long enough, everyone's going to basically have some kind of neurological disorder. And these range from memory loss to brain damage. But the thing that's important to appreciate is that an implantable device can actually solve these problems. I think a lot of people don't quite realize that. But all of your senses, your sight, hearing, feeling, pain, these are all electrical signals sent by neurons to your brain. And if you can correct these signals, you can solve everything from memory loss, hearing loss, blindness, paralysis, depression, insomnia, extreme pain, seizures, anxiety, addiction, strokes, brain damage. These can all be solved with an implantable Neuralink. This is an extremely fundamental thing, and I think a lot of people don't quite understand that. The neurons are like wiring, and you kind of need an electronic thing to solve an electronic problem. So current medical research, we'll just go through what is the state of the art in medical research, and then what's the state of the art in what consumers or people in general can get. So the current medical research has shown that you can read neurons in a human's brain. So there's something called the Utah array, which has about 100 channels per array. But it's like, kind of like it's a bed of rigid spikes that's literally inserted with an air hammer. So that's slightly discomforting, I think. And there's wires and a box on your head, and so it's some infection risk. And obviously, it will look pretty weird if you walk around with boxes on your head. And in order to use it, you have to have an expert medical professional there, and it's only been done in a few dozen people. So, but it is served as an important proof of concept that this can be done. So we did want to point this out and show that this actually does work. It's just not something that the average person could use effectively. And then in terms of what is currently available, there is something called deep brain stimulation, where they put electrodes, a small number of electrodes, in your brain, and will actually zap your brain with an electric current. And it's valuable for its uses, but it can't read or write high bandwidth information. I would say this is sort of a bit like sort of kicking the TV, which does work, but not always, and it has limitations. Nonetheless, this has greatly helped over 150,000 people, and it's actually, just despite being somewhat of a brute force approach, it has been very effective for a lot of people. And this is what's currently available. So we want to radically improve this by multiple orders of magnitude, improve it by a factor of 100, then 1,000, then 10,000. So going into the Neuralink architecture, what we've done over the past year is dramatically simplify the device. So about a year ago, we had a device which had multiple parts, including a piece that it had to sort of sit behind your ear, and it was complex, and you wouldn't still look totally normal. You'd have a thing behind your ear. So we've simplified this to simply something that is about the size of a large coin, and it goes in your skull, replaces a piece of skull, and the wires then connect within a few centimeters or about an inch away from the device. And this is sort of what it looks like. So, yeah. This is our little device. That thing at the bottom is just to hold the threads in place, because they're just like little fine wires. I mean, frankly, to sort of simplify this, what we're, I mean, it's more complicated than this, but it's, in a lot of ways, it's kind of like a Fitbit in your skull with tiny wires. So, and it's, yeah, so our current prototype, version 0.9, has about 1,000 channels. So that's about 100 times better than the next best consumer device that's available. And it's a 23 millimeters by 8 millimeters. It actually fits quite nicely in your skull, because your skull is about 10 millimeters thick. So it fits, it goes flush with your skull, it's invisible, and all you can see afterwards is that there's a tiny scar. And if it's under your hair, you can't see it at all. In fact, I could have a Neuralink right now, and you wouldn't know. Maybe I do. So, and it's also got all the things that you would expect to see, the sensors you'd expect to see in a smartwatch or a phone, like inertial measurement, temperature, pressure. So there's actually a lot of functions that this device could do related to monitoring your health and warning you about a possible heart attack or stroke or other damage, as well as sort of convenience features like playing music. You could do a lot. It's sort of like if your phone went at your brain or something. Yeah, maybe that's not a great analogy. Anyway, so it's also inductively charged. So it's charged in the same way that you charge a smartwatch or a phone. And so you can use it all day, charge it at night, and have full functionality. So you would really, it would be completely seamless. And yeah, no wires. In terms of getting a link, so that, you need to have the device, a great device, and you also need to have a great robot that puts in the electrodes and does the surgery. So you want the surgery to be as automated and as possible, and the only way you can achieve the level of precision that's needed is with an advanced robot. So we're really looking for great people who can help develop both the device and the robot. And we feel confident about getting the link procedure, the installation of a link, done in under an hour. So you can basically go in the morning and leave the hospital in the afternoon. And it can be done without general anesthesia. So in terms of getting a link, like I said, it's essentially you open a piece of skull, you remove about a coin-sized piece of skull, and then the robot inserts the electrodes. We'll talk more about that later. Then the device replaces the portion of skull that was removed, and we basically close that up with actually super glue, which is how a lot of wounds are closed, and then you can just walk around right afterwards. It's pretty cool. So this is our surgical robot. And we actually ultimately want this robot to do essentially the entire surgery. So in everything from incision, removing the skull, inserting the electrodes, placing the device, and then closing things up and having you ready to leave. So we want to have a fully automated system. And to be clear, this robot does actually work. We've used it for all of the implantations. So this shows you at sort of a close-up view, which I think is actually not too gruesome, of the electrodes being inserted in the brain. And if you look closely, you'll see that it's a little counterintuitive that if the electrodes are inserted very carefully, that there's no bleeding. And so if you have very tiny electrodes, and if they're inserted very carefully, so that the robot actually images the brain and makes sure to avoid any veins or arteries, so that the electrodes can be inserted with no noticeable damage. So you will have no noticeable neural damage in inserting the link. Yeah, like you sort of think like if you stab something with a wire, surely it will bleed, but actually at a really small scale, it does not. So does it actually work? And what I'm excited to show you, I call it like the Three Little Pigs demo. And if our animal handlers, we're bringing out the pigs. And what we're going to show you is well, I'll walk right over and show you. So what we have in pen number 1 is Joyce, and she does not have an implant. Obviously healthy and happy. We're trying to get Gertrude out. This is how you know it's a live demo. She's like trying to eat something in the corner of her pen. Come on, Gertrude, let's go. Snacks are this way. Oh man. All right, we'll wait. We'll give Gertrude a second, and we'll move on to Dorothy. Sometimes the pigs are a little shy. So here's Dorothy, and in the case of Dorothy, Dorothy used to have an implant, and then we removed the implant. So this is a very important thing to demonstrate is reversibility. So if you have a Neuralink and then you decide you don't want it, or you want to get an upgrade, and the Neuralink is removed, is it removed in such a way that you are still healthy and happy afterwards? And what Dorothy illustrates is that you can put in the Neuralink, remove it, and be healthy, happy, and indistinguishable from a normal pig. Well, thanks, Dorothy. Man, Gertrude, are you serious? Okay. Well, should we bring them all out or something? Would that be better? How about everyone just comes into this pen? We'll have a few, it'll be a little crowded, but whatever. Okay. All right. Well, is Gertrude still back in the thing? Yeah. Okay, we need to bring Gertrude out. Yeah. Oh, the beauty of live demos. This is a real live demo. All right. Maybe we can zoom in to do Gertrude or something. She's clearly very interested in something at the back of a pen. Can you see her? Or? Not quite. All right. All right, this might take a sec. Well, this worked earlier. All right, well. What if we lift the curtain and then zoom in? All right, here we go. Great. Okay, great. Okay, this is a high energy pig. All right, Gertrude, thanks for coming out. So what the beeps you're hearing are real-time signals from the Neuralink in Gertrude's head. So this Neuralink connects to neurons that are in her snout. So whenever she snuffles around and touches something with her snout, that sends out neural spikes, which are detected here. And so on the screen, you can see each of the spikes from the 1,024 electrodes. And then if she snuffles around, touches her snout in the ground, or you kind of feed her some food, pigs love food, then you can see the neurons will fire much more than when you're not touching the snout. And that's what's making the beeping sound. All right, cool. So as you can see, we have a healthy and happy pig. Initially shy, but obviously high energy and you know, kind of loving life. And she's had the implant for 2 months. So this is a healthy and happy pig with an implant that is 2 months old and working well. Yeah. All right, cool. And then we actually have, I hope this works, so we said, well, what if we do 2 Neuralink implants? And we've been able to do dual Neuralink implants in, actually I think 3 pigs at this point, and we have a couple of them here. And we've been able to show that you can actually have multiple Neuralinks implanted, and again, healthy and happy and indistinguishable from a normal pig. So, so it's possible to have multiple links in your head and have them all be sending out signals and be working well. All right. Phew. All right, so we just showed you a demonstration of reading brain activity. And let's see, probably see that. As I was saying, each of those dots represents a neural spike. And the blue chart at the bottom is showing an accumulation of neural spikes in that region. So in terms of additional brain reading activity, when we have, say, one of our pigs on a treadmill, pig on a treadmill, it's a funny concept, really. And we take the readings from the neurons, and we try to predict the position of the joints. And so we have the predicted position of the joints, and then we measure the actual position of the joints. You can see that they're almost exactly aligned. So we're able, with a wireless neural implant, to actually predict the position of all of the limbs in the pig's body with very high accuracy. Now, in terms of writing to the brain or stimulating neurons, we also need precise control of the electric field in space and time. We need a wide range of current for different brain regions. Some regions require delicate stimulation, some require a lot of current, and you want, obviously, no harm to the brain over time. And the way part of the way we analyze the stimulating neurons is with a 2-photon microscopy. I always have trouble pronouncing that, microscopy. And it's very impressive technology. You can actually literally see in real time how the neurons are firing. So the red sort of things are the neurons. The red sort of flashing things are the neurons firing, or I should say the electrodes firing. So the red things are electrodes firing, and then the green are the neuron bodies responding to the current from the electrode. So you can see them lighting up different brain regions. And then by carefully controlling the electric field, you can actually have one electrode influence possibly 1,000 or 10,000 neurons. So although you might only have 1,000 electrodes implanted, you could be influencing millions of neurons. And this is just a similar chart showing stimulation at different power levels. So, like I said, for the initial device, it's read-write in every channel with about 1,024 channels, all-day battery life, recharges overnight, has quite a long range. So you can have the range being to your phone, I should say. That's kind of an important thing. This would connect to your phone. And actually, the application would be on your phone, and it would be communicating by essentially Bluetooth Low Energy to the device in your head. That's why I say in a lot of ways it is like a Fitbit in your skull with tiny wires. So, and then, like I said, you would not be able to see the device at all. You would look completely normal and just have a small scar under your hair. And we're making good progress towards clinical studies. I'm excited to announce that we received a breakthrough device designation from the FDA in July, thanks to the hard work of the Neuralink team. So I want to be clear, we're working closely with the FDA, and we'll be extremely rigorous. In fact, we will significantly exceed the minimum FDA guidelines for safety. We will make this as safe as possible. Just as with Tesla, while it is legally possible to ship a 1-star car, at Tesla, the only cars we make are 5 stars in every category. So we actually maximize safety, and we'll take the same approach here at Neuralink. And then to emphasize again, what the goal of this presentation is recruiting. We want people who are great at solving problems to join the company and help us complete this device, take care of the animals, write the software, create the chips, and productionize everything. So we need robotics engineers. I think we also especially need people who have worked on and shipped products. So if you've shipped a smartwatch or a phone, or any kind of complex electronics or complex device, or advanced medical devices, we'd love for you to contact us and consider working here. So, and a very important point to emphasize is that you do not need to have prior experience on brains. So a lot of people think, well, I couldn't possibly work at Neuralink because I don't know anything about how brains work. And that's okay, you can learn, but we need software engineering, we need mechanical engineering, electrical engineering, like I said, chip design, robotics, and all the things that a company needs to work. So please send in your resume. Actually, it's not just engineering, obviously everything at Neuralink. So now let's actually move to questions. So we've piled questions that have been asked over the internet, and so we'll do live Q&A. So bring in a bunch of people from the Neuralink team. All right. All right, so if you have any questions, please submit your questions to the Neuralink Twitter account, and we will try to answer as many questions as we can over the next hour. And feel free to ask hard questions, that's no problem, and we'll do our best to answer them. All right, let's move over to the team.
Perfect. Yes, we will continue monitoring questions until the end of the event, so please keep sending them in over Twitter. Elon, do you want to come join us? All right, so the first question is, how is the spike detection implemented? Is it on the ASIC? Is it hardware and software updatable?
Yes. Yeah, I can answer that. So I'm Paul. I work, I've had a few different hats. I've worked a little bit on digital chip design, and more recently working on some of the algorithms, trying to decode the signals from the brain. And the spike detection algorithm, there's historically been many ways of detecting spikes. Typically, people will record data offline and then look for characteristic shapes. But here, we're interested in detecting spikes online. And there's a number of simple algorithms that you can do, for example, like detecting just a threshold. And where we've been interested in doing a little bit better than that. So we actually look for particular shapes, characteristic shapes that we think are spikes. And so we're doing this on the chip. It's for all 1,024 electrodes. There's bandpass filtering that's happening on the chip. So if you think of these as like little microphones sending audio information, we're basically filtering all of that in real time and then looking for these characteristic shapes. You can configure what sort of shapes you're looking for, and that information is what's being sent out. The raw information coming from electrodes is way too much to send out over Bluetooth. So when you're seeing those beautiful spike rasters on the screen, those are the detections that we have coming straight from the chips.
Got it. And just for everyone who doesn't know, can you just explain at a basic level what a spike is?
Sure. So traditionally, people think of spikes or action potentials as the electrical events that happen in neurons and as the primary form of communication between neurons. And so this is a hysteresis event where you have currents that flow and generate this. You can think of it as being a digital signal, a 1 or a 0 that's being sent in time, where neurons will send that signal to often thousands of recipient neurons.
Awesome, thanks, Paul. So I got a question from Toby on Twitter. He asks, what can be further done to simplify the device installation progress?
So we're working on making the device as small as possible, of course, with the robot taking more and more of the responsibility away from error-prone human surgeons. We're hoping to make the process faster and safer.
Actually, it might be good for people to say, who they are and what they do.
Oh, I'm Matthew McDougall. I'm the head neurosurgeon at Neuralink.
Thanks, Matt. Is there anything specifically from the robot that can be done to make this faster and safer and scalable to billions of people?
Yeah, I guess we've started with just implementing, robot manipulating the threads. But we definitely need to expand to essentially doing the entire surgery with the robot. So there's nothing like really, as far as I can tell, fundamentally like stopping us from doing that, sort of like at a fundamental science level. It hasn't been done in the past, I think, probably just because like volumes of surgeries hasn't been needed. But specifically for us to scale up to many hundreds of thousands or millions of patients, we will need to automate like the entire surgery essentially.
Awesome, thank you, Ian. Garrett asks, what are some of the lower bandwidth activities to target first? Is it muscle movement? Is it auditory signals? What level of bandwidth is required for effective use?
So there's a couple of...
Joey,
Just to say who you are and what you do.
Hi, my name is Joey O'Doherty. I'm a neuroscientist and neuroengineer working on decoding from the brain. So there's some low-hanging fruit that I think can really be impactful to help many people's lives, and that's restoring movement and communication in, for example, a spinal cord injured patient. And there's a lot of antecedents in the academic world where there have been very nice demonstrations of doing this, and we think we can take our technology and really bring that to the home, something people can take home with them and improve their lives.
Fantastic. Gil, there's a fun one next. All you.
Yeah, so we're fielding questions from Twitter, so there's going to be some funny comments. First question is, who are you and what do you do? I'll lead with that. And the question is, can the Neuralink chip allow you to summon your Tesla telepathically?
Definitely, of course.
You heard it here first. That's a definite 100%. Carlos, that is the answer.
It's just one bit of information.
Yeah, it's very easy. That's an easy one.
Actually, Max, this might be a question for you. Like some of the questions we had on Twitter was, how do you see the Neuralink device and the essentially API growing over time and allowing developers to interact with the device?
So there's interesting questions long term about whether you do decoding on head or on a phone or on a computer. Ultimately, so at 1,000 channels, it's possible to send all the spike data to a phone and do processing there. As this gets bigger and bigger, you're going to be more constrained by the radio, so you're going to want to push more of this on head, and that changes your programming model. But really, the APIs you're getting either bin spikes or you're getting raw waveforms, and that's like, you can consume it basically like an audio feed.
Yeah, it's worth noting, like the lossless compression of the data stream is about 100 kilobits with 1,024 channels.
Excellent. So this one came up a lot, and this particular question is from Yosef, but will this technology ever be used for gaming?
Yeah, probably.
100%.
Yeah. 100%, yeah.
I think that a good benchmark of does it work well in humans is can a quadriplegic, does it work well enough for them to play StarCraft? I think that's a good functional target.
Yeah. For sure.
Yeah.
Awesome. We'll pull out back from the Twitter questions that are kind of funny. This is a question for the efficacy of the device. Right now, is the device limited to surface layers of the brain only, or can we go deeper? And if not now, what's holding us back from going deeper into the brain?
We are planning on modifying the device and the robot to be able to sew into arbitrary depths of the brain. Right now, we're limiting ourselves only to the cortical surface because that simplifies many of the problems involved with going a lot deeper.
And what kinds of things can you solve on the cortical surface versus when you go deeper?
Sure. So a lot of the low-level processing happens in the cortex in terms of motor intentions, sensory information that comes directly in. So your hearing, your auditory percepts, your visual processing, a lot of that happens in the cortex.
I mean, you could solve blindness. You could solve paralysis. You can solve hearing. You can solve a lot just by interfacing with the cortex. And to be clear, we actually do insert, I guess, about 3 or 4 millimeters into the cortex. So these electrodes are sensing from multiple layers within the cortex. There are deeper brain systems that are underneath your cortex, like the hypothalamus, and I think that is something we'd want to interface with for sure, because that's going to be important for curing things like depression, addiction, that kind of thing, anxiety. But yeah, like I said in the presentation, overall we're aiming for a general purpose device, and really the thing that would change from interfacing with the cortex versus deep brain systems is kind of the length of the electrode. So we just need kind of longer wires and to adjust the robot in order to access deeper regions of the brain.
Awesome. Ian, did you have
even now,
anything
I'd
to
say
add?
the robot is designed, like the full length is like 7 centimeters or 8 centimeters. Yeah.
Yeah, so right now we're designed for like 6 millimeters. The actuator itself isn't actually limited to 6 millimeters. It can go much deeper. That's sort of, in addition to scaling out sort of to the rest of the surgery, also scaling to deeper, which is mostly a sensing problem. So the ability to avoid deep vasculature is sort of an interesting problem that we're working on in the robotics world here. So yeah, lots of cool problems in the robot.
And you're leading robot engineering.
Yeah, sorry, I'm Ian. I lead the robotics program here.
Robot is a man's best friend. All right, next question is, what is the most challenging problem that must be solved in order to meet Neuralink's ultimate goal?
Well, I think one of the hardest problems is kind of, I'd say, material science and especially the installation of the electrodes. What would you say?
Yeah, absolutely.
Also, you want to introduce yourself?
So I'm Felix Deku. I currently lead the microfabrication team. My team makes up of a group of process engineers and material scientists. And our job is to make the tiny wires, as Elon referred to them, what we call the threads that are implanted in the brain. And of course, the threads are made of conductors and insulators. And choosing the right material that is amenable to the brain and compatible to the brain is something that our team have expertise on, and we work seriously on interface engineering just to make sure that our layers are actually well thought through, well designed, and at the end of the day, when we implant this device, they'll be actually functional for either reading or for writing in the brain.
Yeah, and I think it's going to be important in terms of material science problems is making sure that the threads, the electrodes, can last for decades in the brain, which is a tricky thing because it's a very corrosive environment, and you're in a dichotomy where you want to read and you want to sense electrical signals and you want to generate electrical signals, but you don't want to corrode the electrodes over time. So you need to have an insulating layer that is very robust, but also very, very thin. It has to be just the right amount of insulation, and it has to stay that amount of insulation over time. So this is why I think we think probably like a silicon carbide type insulator is probably the best long term from a material science standpoint. But silicon carbide is a tough material to work with, but that's probably the right choice long term. Would you say?
Yeah, I totally agree. And it's also, apart from its electrical properties, it also helps with adhesion between the metal layers and the polymer substrate. Another thing that we're also looking at is, since we're actually reducing the electric dimensions, the electro side, the actual side that actually speaks to the neuron, also have what we call high resistance to the signal. So we actually look into like material engineering that will reduce the impedance at that interface, so that we can actually have a very small electro side but still be able to speak clearly to the neuron.
And when you guys say thin, how thin?
How thin? So one strand of your hair is about 100 microns in diameter. We can think about dividing that into 20. So one of the thickness that we recognize is about 5 microns, and we have this possibility to go even thinner in the nearest future.
Yeah, we think we can probably go sub-micron in thickness, but obviously, as the thinner you make the wire, the harder it is to sense the signal and to do stimulation, because there's less cross-sectional area for the current to traverse. In terms of upgrades, that's part of why I wanted to show the explanted plig, is to show that you can actually take the device out, and there's no observable behavior change. The pig is as happy as before and healthy, and I think this is going to be important for upgrades, because obviously if you get an early device, then by the time, let's say you get version 1, probably by the time we have version 3 or 4, you want to upgrade. You wouldn't want version 1 of a phone, and 10 years later, everyone's got version 3 or 4. So it's going to be important to be able to remove the device and upgrade it over time. So over time, the Neuralink would do even more than it did before.
Awesome. So here's a question about the device. We have been talking a lot about read speeds and we haven't talked about read or write speeds. DJ, what are the read and write speeds of the device, if you think of it like a computer?
Sorry, when you say speed, what do you mean?
Like, how quickly can you read information from the brain, and how quickly can you write information in the brain?
Okay, so let's see. So one of the things to highlight is that we...
DJ, what do you work on?
Yes, my name is DJ Sa. I'm leading implant electronics development.
Like a chip design.
And a chip designer, electrical engineer.
Yeah.
The prototype that we were showing, it has 1,024 channels. All of those channels are capable of recording and also stimulating. And in terms of recording, as Paul mentioned, we do have on-chip algorithms to do a level of compression and extracting the signals of interest, in this case, spikes, neural spikes.
Sure.
And those things are actually happening at a much faster speed than your brain even is processing those information.
Well, do you want to say like things like time resolution, like within how many milliseconds can you detect a spike, and what's the just some technical data?
So in terms of the signals that we're collecting, we're digitizing them at 20 kilohertz. Generally, the signals of interest are anywhere between about a millisecond in width, and so we sort of sample it at 20 times that speed. And we have analog to digital converters that divides that into 1,024 levels, so 10-bit resolution. And the spike detection is done in less than 900 nanosecond, which is really, really a fast time. And it's only sort of determined by the speed of the clock. And for making sure that our implant is low power, we're running them actually at a very slow speed. And then for stimulation, we can actually create any arbitrary waveforms with about 7 microsecond of resolution. So basically, whatever you want to draw, we can stimulate and generate those pulses through any combination of our electrodes.
And this is just version 0.9, or aspirationally version 1. As we go to version 2, 3, 4, these things will expand, I think, ultimately by orders of magnitude, many orders of magnitude.
Great. Everyday Tesla asks, how big is the Neuralink team, and how much do you expect it to grow in the near future?
We're about 100 people right now. I think over time, there might be 10,000 or more people at Neuralink. So I think, yeah,
Couple orders of magnitude.
yeah, exactly. A couple orders of magnitude. Those are my favorite phrases. Yeah, just, a couple orders of magnitude is no big deal. So, yeah, probably the number of electrodes will grow with the number of people at the company.
Hopefully that's a super linear relationship.
Yeah. Well, we might need a million people at the company then. Yeah, super, yeah, even more. Yeah. Ideally, super linear.
Our hiring quotas are determined by our channel counts.
Yeah. Maybe it's 10-to-1 ratio or something.
Yeah.
Cool. So Twitter asks, how does the implant system fare against various disturbances from the outside, like electrical, magnetic, Wi-Fi, radio?
Yeah, so the current version of implant that we have is using Bluetooth low energy radio. So similar to any Bluetooth devices that are out there, they are able to coexist with other devices that are using and sharing our same spectrum in 2.4 gigahertz. Obviously, as you imagine, when you go to concerts or there's just a lot of people, the signal quality does degrade because it is a pretty congested spectrum. So we are actually working on some new versions of the radio that are operating at different frequencies to be able to also send out a lot more data and have it be scalable to millions of electrodes. And then also in terms of sort of electromagnetic compatibility and interferences, obviously it's very important for us to coexist with other systems and just disturbances out there. So there are also well-documented guidelines from FDA that we'll be following and doing a lot of testing for.
Fantastic. We are going to take an audience question. Fred, take it away.
So we all want to play StarCraft using Neuralink, but what are some likely first applications?
Well, I don't know if we all want to play StarCraft.
There are other games.
There are other games to play. Exactly.
But also StarCraft.
Yeah.
So our first clinical trial is aimed at people with paraplegia or tetraplegia, so cervical spinal cord injury. We're going to enroll, we plan to enroll a small number of patients to make sure the device is safe and that it works in that case.
Yeah, so actually just to elaborate on that, if somebody is like a severe spinal cord injury, to the degree that they have very limited control even over their facial muscles, then but with this implant you can actually think just by thinking you can output words, and you can type, and you can control a computer, control a phone, and which is pretty wild. And I think something that's very exciting as a long-term application is if you can sense what somebody's trying to do with their limbs, what they want to do with their limbs, then you can actually do a second implant that's at the base of the spine or wherever, just after wherever the spinal injury occurred, and you can create a neural shunt. So I think long-term, I'm confident that long-term it will be possible to restore somebody's full body motion. So if somebody even has a severed spine, they will be able to walk again. They will be able to use their hands. And like when you have a severed spinal cord, you essentially have broken wires. And so if you can just jump over those wires and transmit the signals over those wires, you can give somebody the ability to walk again, naturally.
So DJ, you talked about outside interference. Can anyone talk about the inside interference? So how to protect the implant from the body?
Sure, I can talk about that. My name is Robin. I'm a mechanical engineer, and I lead the implant mechanical packaging and assembly team. So actually making the devices and designing the seal. So yeah, the body's not a friendly place to be. So what we do is basically create an accelerated test chamber that can mimic the conditions that the devices will see in the body, and basically test the devices at as fast as accelerated rate as we can. At this time, we're limited temperature-wise by some of the electronics components, but basically we can test subsystems to mimic the environment in the body, and by that, we've brought some devices in the tester right now to almost a year, and all the implanted ones prior to these implants, we had tested the same architecture in the tester to validate it. And yeah, so there's obviously chemical things attacking the implant. There's pressure. There's mechanical shock and vibration. So all of these things are part of it. And yeah, I think one of the things that really helps is having everything in-sourced in-house. So we have the capability to deposit thin layers of metal. We have the capability to weld glass and machine micron scale with lasers. And yeah, so basically we have all the tools in-house to be able to design any sort of sealing, enclosure, packaging that we need to do.
Awesome, thank you, Robin. Another question from Twitter, will you be able to save and replay memories in the future?
Yes, I think in the future you will be able to save and replay memories. I mean, this is obviously sounding increasingly like a Black Mirror episode, but well, I guess they're pretty good at predicting. But yeah, essentially, if you have a whole RAIN interface, everything that's encoded in memory, you could upload. You could basically store your memories as a backup and restore the memories. And ultimately, you could potentially download them into a new body or into a robot body. The future is going to be weird.
Cool. So I can't help but notice that the pigs back there are pretty well behaved and pretty darn cute. Can anyone talk about, I'm looking at Autumn over here. First, can you tell everyone who you are and what you do here? And can you describe, like, how are they so well behaved and so smart?
Well, I'm Autumn, and I lead our animal care program. And our philosophy here is to set up a system where the animals are able to volunteer, to make choices, to participate in our projects. As you see, sometimes they choose not to participate, and that's okay. We want to make sure that our animals are happy and healthy. So all of the behavioral research that we do is led by positive reinforcement. And again, that allows for them to choose to volunteer or not.
Sam's also on our animal care team. Sam, do you have anything to add to that?
Hi, I'm Sam, one of the veterinarians here. Work closely with Autumn, taking care of the animals. And yeah, it's just emphasizing what Autumn said, the whole animal care program here. In fact, the whole company here is very dedicated to promoting the care of these animals. Everybody's involved. Everybody's very interested in making sure that they're taken care of. And yeah, the program from top to bottom is designed to make sure that they can express their species-specific behaviors, choose to do things. We don't force things upon them as much as possible. And yeah, that's why you see the pigs happily rooting around the straw right now and generally being very content.
They do have those natural little smiles on their faces, which is ever delightful. Next question is, what programming language are you guys using for developing the device?
Several. Yeah, we use several different types of programming languages. So for chip development, a lot of Verilog for doing low-level programming at the kind of the register transfer level. As you go up higher and higher, there are various C, C++, Python. But to be honest, like at the end of the day, it's not which programming language do you know how to use. It's do you know the principles behind coming up with just methods to enable these systems to work. So I think if you have any experience in programming and you've been building things since you're little, you should really come join us.
Yeah, but can I play Crisis?
Eventually.
It can play Crisis.
Cool. Crisis confirmed. And then Ian, what about Ian, what about the robot? What kind of programming languages and tech stacks are you using over there?
I mean, sort of just reiterating what DJ said, sort of doesn't matter. Like specifically for us, there's a real-time low-level platform, C++, some Java and Python scripts. But really, those are more just like pragmatic choices to essentially optimize for getting like productive work done. So it doesn't really matter what your background is or necessarily what the tools you use are. It's more just, can you like accomplish things really quickly?
Awesome. This next question is from This Is Rex. They're wondering, can this device be used to explain consciousness? In the long term, of course.
I can certainly shed some light on consciousness.
This is a really interesting question. I think the answer is yes. And I think one of the reasons that consciousness is so hard is because, like anything in physics, you're looking at a mapping from X to Y, where X is the neuronal correlate, it's the thing that's happening then physically, and then Y is this phenomenal state. And historically, we've been unable to observe the neuronal correlates very well, and unless it's in you, we've been unable to observe the phenomenal state. So as soon as neuroscientists are able to personally get these tools where they can see the correlates and they can have the experience, I think the hard problem will vanish very quickly.
What I find remarkable is that the universe started out as like quarks and leptons, we'll call it like hydrogen, and then after a long time, well, what seems like a long time to us, the hydrogen became sentient. It gradually got more complex, and then but we're basically, hydrogen evolved, and somewhere along the way, that hydrogen started talking and thought it was conscious.
I like the joke that it turns out that if you bombard Earth with photons for long enough, it'll emit a Tesla.
Yeah. Exactly. Yeah, that's exactly what happened.
Just basic science, guys.
Yeah.
It's just
they
science.
teach you in school. Yeah, so there's a lot of Twitter comments coming in about a question that I think is on everyone's mind, no pun intended. What is the security of the device look like? What kind of precautions are being taken, and what does the future look like for the security of the system?
So first and foremost, privacy and security are top priorities at Neuralink, especially given the sensitivity of the data that we're collecting. And one of the things that we're ensuring is to make sure that a lot of the interactions with the brain data is going to be encrypted and authenticated properly. And I think this has been kind of a sort of recurring theme, but one of the things that we have the ability to do at Neuralink is that we work on every layer of the product, from chip design to source code, and it really gives us a unique opportunity to embed security as part of our design from the get-go, and to make sure that there are no single points of failure. So as an example, we can actually completely isolate sensitive modules like the BLE radio by just segregating it out at the hardware level, and really making sure that we protect the I/O to the brain away from any potential attacks, and really minimizing the attack surface. And we have in-house security expertise, and we're also working with external parties to do audits and perform penetration testing.
Excellent. Thank you, DJ.
Well, actually, is there a point that anybody here wants to make that has not been asked in a question, but you think should be a question? Anyone? Yeah.
So hey, I'm Zach. I work on the microfabrication team. I help making implants. And one thing that I think is really cool, just in general, is that this is a platform essentially, so we can change the design up in a variety of ways. So if we find that a certain design or electrode size or number of electrodes works better in different areas of the brain, we have the capability to do that. I personally think that's very cool.
Fantastic. Anyone else? Dan, do you have something to add?
Yeah, I think one of the things that's allowed us to make such fast progress in the last few months is the use of pigs as a model. And we started out choosing pigs because of the very similar anatomy of their skull to humans, same thickness and similar kind of membrane, dural membrane. But then as time went on, we realized that pigs are actually have amazing other properties. You can train them to walk on treadmills. You can train them to do all kinds of tricks, and also that they have this large representation of the snout in the cortex, which you can very easily stimulate. So the question would be, why are we using pigs? And I think we've even surprised ourselves at how useful they are as a model in this respect. And another important point is that it's very easy to keep pigs happy. They have very low needs, and so we can build an environment in which they have amazingly good welfare.
Yeah,
You seem very happy about food.
yeah, it's easy to make pigs happy. Basically, they love food. Pigs really love food. This is a true thing about pigs. Um, you know, that they're yeah, give them like sort of some straw and some things to play with and some friends to hang out with and good food, and they're happy as pigs. And then yeah, pigs are actually quite similar to people. So that's you know, if we're going to figure out things for people, then pigs are a good choice. And they're quite robust creatures, like little tanks. And then I think one of the questions was like, what if, like is the device itself robust? And it's like, well, you know, pigs, they bustle around quite a lot, and they bump into things, and they headbutt each other at times, and they're pretty animated. So if the device is lasting in the pig, as it lasted there for 2 months, and still going strong, then that's a good sign that the device is robust for people.
Fantastic. One common theme that's been coming up a lot on these Twitter questions coming in is that of availability. And so Matthias has a specific question on this, which is any estimate of how much it will cost at launch and what price it will reduce to over time?
Well, I think at launch, it's probably going to be, I would say that's not really representative, because at first, I think it's going to be, you know, quite expensive, but that price will very rapidly drop. And I think over time, we want to get the cost obviously down as low as possible. But I think inclusive of the automated surgery, I think we want to get the price down to a few $1,000s, something like that. And I think that's possible. I think it should be possible to get it similar to LASIK, and then the device electronics itself, I think will not be very expensive, because it actually does use a lot of the parts that are made in extremely high volume in tens of millions of units for smartphones and smartwatches and wearables in general.
Great. So here's another question about the device. What does the architecture look like? Is it a CPU, ARM CPU? What's going on inside the device that you can talk about, DJ?
I can talk a little bit about the digital architecture. It's fully custom. One of the most difficult challenges, I think, of building an implant is the energy density. So the more electrodes you record from, the more energy you're going to be consuming. And so there was nothing commercial out there. So there's an analog front end that's able to amplify these really small signals, like microvolt range, so that we can actually digitize them, and then take those signals and then find exactly what we're looking for. And there was nothing out there that could basically do those two things, and so that's why we had to build a full custom ASIC. And so there's really, there's nothing out, like it out there. It's designed specifically to record signals from the brain, and anything else would just be wasting energy.
Yeah, so the thing that I would add to that is, so there are obviously elements that we customize from ground up, like our neural amplifiers and some of the algorithms that we develop, but a lot of the other systems around it are really borrowing from parts that are already been productionized and available from the wearables industry, so BLE radio, a lot of the low power microprocessors that are part of it, a lot of small sensors. So there are obviously the neural sensors that we're developing that gives us kind of a unique data set for our applications, but really a lot of that is getting packaged up and just not really resisting the industry that's been sort of been laid out to really create these devices with very short amount of time.
So here's another question about the integrity of the device, more from a mechanical perspective. So you're replacing a piece of bone and replacing it with an implant. And then the person is going to take that home. How does the integrity of the device fare compared to, I don't know, bone or something similar?
Sure. Well, I think Matt's probably replaced a lot of pieces of skull with plastic and other materials. So I don't know if you can talk about some of those. But yeah, basically, I mean, we know that what the mechanical properties of bone are, and we know what the stresses on the device are going to be. So it's fairly easy to just go from first principles and design for any condition that it might see.
Yeah, I mean, as you can see from the pigs, as I was saying earlier, the the implants are obviously very robust because I mean, pigs move around vigorously. They roll around. They bang into the wall. They bang into each other. They do like headbutting, and way more than people do. So, well, sure. But you know, like it's not like the pigs are just walking around very delicately. They're high energy creatures, and I think it's clear that the implants are, you know, has been going for a few months, still going strong, despite a lot of vigorous activity from the pig. And it's difficult. You can't just explain to the pig, hey, you've got an implant in your head. Why don't you take care of it? So it's got to be robust against you know, a lot of head impacts, essentially. So you know, I think maybe one of the things that isn't super obvious is that the implant itself is attached to the skull, but the electrodes have long threads. So you can have quite a lot of movement, relative movement between the brain and the skull without putting attention on the electrodes that are inserted in the cortex. So, well, let's see. With that, maybe a couple more questions, or if anybody wants to make some comments, and then we'll call it a day.
So I just want to add to what you just said. So the thread is actually also in the brain, also because of their thinness, they're actually very flexible. And so as the pig is moving around and banging their head, the threads actually move with the brain, even the normal pulsation of the brain. And that help minimize stress within the brain tissue also. And that has a long-term impact on the functionality of the device.
Zach, how long are the threads?
Well, right now they're about 43 millimeters, but like I said, it's tunable. So if we want to hit deep brain regions or some other brain area, like we totally can do that.
Just to follow up on what Felix said about the threads moving around with the brain, I mean, that's great for protecting the threads, but it equally serves to protect the tissue around it. We have a lot of different ways to image the tissue around the threads and iterate very quickly on doing things to them that will improve the overall biocompatibility.
As a closing question, I thought we might go down the line starting with Dan, and what I'm wondering is what is the #1 thing on your wish list that you're really hoping that the Neuralink device will do over time that you're working towards?
So my background is in visual neuroscience, and one of the things I think has great potential for the Neuralink is to provide a visual prosthesis for people who have retinal injury or blindness through eye injury. You can essentially plug a camera directly into the visual cortex and stimulate with an enormous array of thousands or maybe tens of thousands of electrodes to recreate a visual image. And in time, perhaps you can use that same technology in people who haven't lost vision to produce some kind of heads-up display, something like Terminator or something like that.
Wonderful.
In fact, it's worth saying that, like, over time, we could actually give somebody supervision. Like, you could have, like, ultraviolet or infrared or see and radar. You could basically name your frequency. You can just dynamically adjust the sensor or have sensors that feed into the visual cortex across a wide range of frequencies and actually have superhuman vision.
Yeah, so for me, telepathy. So I think it's incredible amount of effort to put your thoughts into a set of words, and you know, it comes out completely compressed. So being able to do that seamlessly without being able to compress it with all of the mechanisms would be great.
Yeah, it's like just I'm sorry, to add further to that. In fact, when I did the Wait But Why article, I think Tim thought I said consensual telepathy, but I said conceptual telepathy. I would presume it would be consensual, because you definitely don't want just people, you know, sending stuff into your brain without your consent. But a lot of our brain thought capacity goes into compressing our thoughts into words. And then you think of like the data rate of words. Words are a very low data rate. And we're putting a tremendous amount of mental energy into compressing the concepts and thoughts in our head into words, and then slowly talking. Speech is so very, very slow. And we could actually send the true thoughts. We can basically have far better communication because we can convey the actual concepts, the actual thoughts, uncompressed to somebody else.
So non-linguistic, consensual, and conceptual
Yes,
telepathy.
exactly. Non-linguistic, consensual, conceptual telepathy.
There we go.
Rolls off the tongue.
Yeah, I've actually been excited from the beginning, sort of about the side benefit of these devices. I sort of see them as essentially like an oscilloscope to a printed circuit board is our device to the brain, where just by virtue of having this in there and being able to see what's actually going on, you'll end up learning a ton about how the brain works. And so sort of augmenting people, but also just using that to learn a lot more about neurological diseases is really exciting to me.
Absolutely.
So to sort of follow up on Elon's thought, I feel, and I imagine a lot of other people feel the same way, that there's a lot of sort of trapped creativity in your mind. You can, for example, close your eyes and conjure up like an incredible, Dali-esque scene. But if I wanted to actually show someone that, it would take years of honing a craft to be able to paint that. And so, potentially with enough electrodes in the right places, you could begin to sort of tap into those raw concepts or thought vectors and be able to decode that and show people. It could be for art, you imagine music, or even for engineering, like a three-dimensional model. And
So mental artistry is a new field.
I like to think about ways to interface devices with biology better. And so one of the things I'm looking forward to is getting this thing to be less like technology and more like biology, so that it really is seamlessly interfaced with the brain, stable for a very long time, and then similar to that, having stimulation be much more precise and multidimensional, such that eventually the brain sort of doesn't really know if it's being stimulated from outside or inside, and you end up just sort of completely merging.
Wow.
Yeah, following up on stimulation, one of the things our device can do is simultaneously read and write on every channel, stimulate and record. And that's, both a more challenging problem than it may seem like at first, but also, incredibly exciting, the sort of the vistas that it opens up. I mean, it's really kind of the whole game in terms of interfacing with the nervous system, and I'm very excited to use that.
Yeah, I'm excited just because of the scalability of the device. We're doing everything in-house, and all of it can scale to more channels, more brain regions, et cetera. I think, I'm really interested about solving things related to anxiety or depression, or even removing fear. I'm an athlete, and to rock climb without fear would be pretty cool.
Maybe you need a little bit of fear.
Yeah, just a little. And also, it'd be great if we could make the pigs fly, but
I think we have an incredible opportunity to limit human suffering to a tiny fraction of what it is today, in all kinds of different avenues. Pain being the essence of suffering, we might be able to control that finally, and so many other diseases, so much other suffering in the world. I think the Neuralink device could help a lot with.
Amazing.
I think all these things are great functions for a Neuralink. I think on a species level basis, I think it's going to be important for us to figure out how we coexist with advanced artificial intelligence, and I think achieving some kind of AI symbiosis where you have an AI extension of yourself, like a tertiary layer above the limbic system and cortex, and having that symbiosis be good, such that the future of the world is controlled by the combined will of the people of Earth. I think that's obviously going to be the future that we want, presumably, if it's the sum of our collective will, and so I think it's going to be important from an existential threat standpoint to achieve a good AI symbiosis, and that's what I think might be the most important thing that a device like this achieves.
I have, in many ways, a very basic science interest, which is I'm really interested in the nature of consciousness, and there's a lot of very silly philosophy that's been written about it over the last 1,000 years. But I think that we've been very limited by the tools and our ability to interrogate and measure the brain. And as these tools get better, it will pull it into the realm of physics, and it's really one of the last big, great mysteries in science.
So for me, can you imagine a disease-free future? A future where you know what's going to happen to you before it happens, so you can prevent it. With these devices, we'll be able to not just pick up electrical signals, but we can also pick up chemical clues in the brain. And if you're successful, which I know we are, we'll be able to kind of prevent ahead of time, diseases. And really, the functionality of this device is widespread. So I'm looking forward to the future.
I'm really excited about the opportunity to help people overcome challenges that they face through life circumstances, bad luck, through no fault of their own, spinal cord injury, brain disease, some devastating things that completely change your life. Hopefully we can help them get some function back.
I know and love many humans with autism spectrum disorder, so I'm really interested to see how the Neuralink might be able to support them if they chose to do that.
Yeah, so I mean, everyone else along the line has had amazing ideas and suggestions, and for me, it's about memories, and everyone loses those memories over time. I already can't remember what happened to me when I was younger, and it'll only get worse. And so, having a repository of memories that you can access whenever you want. If you're feeling down, you can go access some good memories. If you miss something or you miss somebody, you can go and access those memories. And I think that would just be such a life-changing experience to be able to just tap into that.
Those are such a beautiful and diverse array of answers there.
Yeah. All right. Well, thanks for tuning in. And as I said, please consider working at Neuralink and helping us solve these problems. There's a tremendous amount of work to be done to go from here to a device that is available, widely available, and affordable and reliable. So please consider joining us and supporting us in our mission. Thank you very much.